So then today I asked our PhD student Chuyin to give a presentation on his word-based quota structure characterization, and I invited people in quota structure because this word-based characterization can be useful for as an alternative to similarity-based characterization of the quota structure, which we have been doing so far. And the format-wise, we plan to ask the Chuyin to give a presentation roughly like 25 minutes. And during that time, we'll make the presentation quite accessible to anybody. And you can ask any kind of clarification questions, but if it's a detailed question, then please hold it until the second part, which we will restart after 5 minutes of the break. And then during the 5 minutes, you can decide whether you want to stay for the further discussion or go back to your work as well. All right, go ahead.
Okay, so I expect this might be longer than 25 minutes because I just added something right before the meeting, so we will see. Yeah. So hello everyone, thanks for coming. And today I'm gonna present my the work I'm currently doing. And so I'm trying to decode natural scene images from some freely reported descriptive words. And so at the beginning, I'd like to let you experience the task, the free report paradigm. So the question. Okay. So I will briefly show you a natural scene image. And the task is to describe the image with some words.
Maybe everybody can type the words in chat box.
Okay, so it will begin 3, 2, 1. So that's the question.
It was too fast.
Too fast. Okay, so 3, 2, 1. Yeah, that's okay. That's very good. Thank you. And now I will show you another image, and the task will be the same. And what word will you use to describe the image? So 3, 2, 1.
Oh, okay.
Yeah, very good. Thank you for participating. And that's how we collected the response words. And I will also give you some background information. So this is in 2022, we published a study in which we asked people to freely describe some natural scene images after briefly seeing them with masking. So in the demo, I didn't show you mask, so it was a bit easier than the real task. And that's the original study. And then based on the report frequency of words, we calculated an index to quantify whether to describe the word, the feature of words. But that's not my point, so I will skip this part. And last year, Beat Mudrik and her student tried to replicate study adding black and white and blurred images. And now I reviewed the paper, and we are currently writing a commentary or say a response to their replications. And so as you can see here, this is the intact image and blurred version and black and white version. So they have 4 experiments with different names. You don't need to remember those names. But just to say that they mainly focused on the hardest condition, where SOA was 67 milliseconds. And there is a key difference that they did not force participants to type in 5 words. We did that. We forced participants to give 5 words, no matter if they can give or cannot. So in their task, there were some empty responses recorded. So Francisco?
Sorry, maybe I didn't understand this before, because you asked which words we would use to describe the picture, but the original task was write 5 words about the picture, and
Yes.
they didn't do that. So you ask 5 words, minimum,
Yes.
maximum, like not minimum, not up to 5, like 5.
Sorry, so in the original task, as you can see here, we have 5 blanks, and participants are forced to type in 5 words to fill them all before proceeding. Yeah.
Okay. So sorry. Thank
you. Okay. Thank you. Yeah, but in their task, they didn't force that. Okay, and in their paper, they made some criticisms that we don't agree. And today I will focus on one comment. So they claim that the paradigm failed to capture aspects of conscious perception. And in their paper, they used the term free report paradigm and the calculation of index interchangeably. However, the words are a measure of experience, but the index is a measure of the word. So these are different levels of measurement. And as a part of the response, I will show what the free report paradigm, or say the descriptive words, can do. That's the point today. And to give you an overview, if we have a large stimulus site, say here in our case, we have around 400 natural scene images. And the question is how to characterize these stimuli. And we can collect pairwise similarity ratings, like some people in our lab are doing, but that task might be very resource consuming. You should have, some of you should have that experience. And if we collected detailed descriptions for each stimulus, for example, Fei Fei et al. had such kind of study in 2007. And in their study, the analysis of such data can be very complicated. So here, a few descriptive words might be a good trade-off for our purpose. And after the task, what we have is like this. For this image, 10 participants saw that image, and each participant gave 5 response words. So like here, so we have 50 descriptive words in total from 10 participants. And we will transform the words into a similarity matrix. So how to do it? We put the words into a word embedding model. Here we are using this commonly used model called GLOBE. And a word embedding model creates a very high dimensional semantic space. So in this GLOBE model, we have 300 semantic dimensions. And each word is associated with a vector in that space, which represents the semantic meaning of that word. And the data is like this. So 300 numbers, one number on each dimension. And we can calculate it. We can calculate the centroid, or in other words, mean vector of the words under an image. In that case, the centroid of word embeddings means average representation. It performs well in predicting similarity in text analysis shown by some previous studies. And after that, we can calculate the cosine similarity between any pair of the images, and then create a similarity matrix based on that. So that's what we have. And I had an axis because there are over 400 images, and so you can see the heat map here, and also MBS clustering results. But is this a valid methodology? So just after seeing the heat map and MBS plot, it's how can we know whether or not this is a valid methodology? To me, this cannot tell much. I think this cannot tell much. And probably because at level of verbal reports, natural things are a loose cluster. So like this from Hall and Tononi, 2024, these two images, of course, they look very different. But when you are asked to describe them with words, you will probably give similar word descriptions. So how to check the validity of methodology? We try to classify which image a participant is seeing by their response words. So there are a number of descriptive words under each image. We calculate the centroid for each image. And during that process, we implemented a cross-validation. So under each image, 10 participants saw that image. So we compare between one participant and the other 9 participants. So we can do this, we can repeat this 10 times, giving us 10 comparisons in total. So it's like for this example, we compare participant 1 with participant 2 to 10, the other 9 participants. So we can do this comparison 10 times.
Wait, can I just ask what you mean by compare?
By compare?
Yeah, what do you mean by compare?
Yeah, it's to okay. Can I answer that question after next slide? Okay. Yeah. So yeah, we have one participant reported 5 words under an image, and we calculate the centroid of the 5 words for that participant. And based on that centroid, using that centroid, we can calculate cosine similarity between the both centroid and the centroids of all the 420 images. Which
each of the whole.
Yeah, each of the 420 images.
Right.
That gives us 420 similarities.
Unequal.
Sorry, can you remind me what is the centroid?
Yeah, the centroid is from the word embedding model here. So for each word, we have a vector of that involves 300 dimensions. That means a point in a 300-dimensional space. And the centroid is the midpoint of some words.
It's a center of the gravity.
Yeah, center of, so if one word is a point and we have 5 words, then we can find the center point.
So in what ways? Is it about like meanings, like a semantic thing, or is it like another aspect of the word, of like how frequent it is used in English language? In what aspect is this a center of gravity?
So to interpret that centroid, it means average meaning. So it's like it's a average semantic meaning. Yeah.
There is potentially no corresponding single word, right? Like, here, Chuyin is representing it with 4 words with a 2-dimensional space, right?
Yes, and if we find, so suppose we have a 2-dimensional semantic space and each word is a point, we find the centroid means it's just the central position of these 4 words in this semantic space. It means the average semantic meaning of these 4 words.
But it may not
Okay.
correspond to any existing word at all.
That's all right. I'm just still unclear. Like, is this about the meaning, or how did they extracted these embeddings, or these, like, is it like they just looked at a bunch of text and looked at how these words are used?
Yeah, so a word embedding model is trained based on a very large corpus, like every say all the text from Wikipedia or all the text from Twitter, and I think the algorithm is based on co-occurrence.
Yeah.
Co-occurrence probability.
Yeah, Zoe is also putting it in the chat.
Yeah, co-occurrence. Yeah.
So basically,
Okay.
if the 2 words co-occur very often, that means they're closer in meaning, and their vectors will be closer to each other in terms of like the angle.
Yes.
But
So,
that's not
but then
our methodology. It's just one choice of the word embedding model.
Yeah, there are many other word embedding models based on different library, or maybe they have different training methodology. Yes.
I think that the validity of this analysis is probably better illustrated once you show the results, right?
Yeah.
I think that's the so maybe we can probably hold off that discussion, detailed discussion later.
Yeah. So okay, so we got 400 cosine similarities based on the centroid of one participant, and all the each of the 420 images. And we can do a k nearest matching, where k is a preset number. So we rank the similarities and see if the correct answers is in the top k similar images. And here, so Angus, it's your question still there?
Keep going, I think.
Okay. And here are some results. So the left-hand side is from our original data set, and thanks Liad and her student who provides a lot of additional data, we can do the same thing on their on the response word collected by them. And the right-hand side is their results. So we can see that the matching rate, under the most strict condition, which is 67 millisecond SOA and k equals 1. And under this condition, we can see the performance is much better than the chance performance, but it's not that good. And it's not very good, I would say. Yeah, it's around 10%. But you can see that on the right-hand side, except this blue box, which is 267 milliseconds, called long exposure. So the other 3 experiments of 67 milliseconds SOA showed a much better performance compared with our original results. So why is this? Remember the key difference I mentioned before. The replicative experiments did not force participants to type in 5 words. So if one is not confident in the description, they might not type it in. So it's possible that their studies only collected the most confident responses. And to check that, we weighted the words by confidence ratings and get the recalculate the matching rate. You can see on the left-hand side is the without confidence rating, and right-hand side is the results after weighted by confidence ratings. You can see, by the way, this is k equals 1. And you can see that the performance improved a lot. It's almost double, but it's still a bit worse than Liat's results. And what are the potential reasons? There is another difference that okay, Chen. Yeah, I think Chen has a question.
I have been a little lost since you introduced the analysis, but sorry, can you go back to the analysis method slide where you talk about centroid and then K nearest matching rate?
Here?
One participant, 5 words. Next one. And I have one. Yes, here. So first of all, my understanding is you compute a centroid for one participant under one image.
Yeah.
And how many participants per image?
10 participants per image in total.
So you have 10 centroids per image.
Yeah.
No,
this involves some technical details. So for each comparison, and here we have a centroid. Let me find. So we have a centroid for this 5 words for this participant, and
Yes.
we have a centroid for all these 45 words as the centroid of the image. And like this, we have a centroid for each of the 420 images based on 45 words per image as the, say, criteria or training data set. Yeah.
So in other words, we use always 9 participants per image to generate a training set. And then training set is 1 centroid per image.
Yeah.
So you have 1 point per image, and then something that you have never seen before, which is this test image, a test response, and then you find which of this training, this test image, test report is most close to.
Oh.
Exactly close to the original image that he counted as a match.
Yeah, when K equals 1. That's
I understand. So you do this for
all the images.
so
Yeah,
for each of the 420, you pick out 9 people, generate
Right.
cent, so they have 420 centroids, each
Right.
represent one image. So that's the training set. You train the algorithm, and now you move that to test and find that one participant for each image. And if they can find it within a certain criteria, with K equals 1 being the strictest, and then K equals another bigger number being the lenient, then it means the algorithm is working or not in certain cases. And then, okay, I got it.
Okay.
Thank you.
Just while you're on this slide, you talked about weighting the words by confidence.
Yeah.
So I just want to ask in this example with participant 5, those NAs, which probably means not applicable, which means I couldn't think of the word. Would that be associated with high confidence or low confidence?
Low confidence.
Low.
Yeah, I didn't show the confidence rating here, but yeah, this each word is associated with a different confidence rating. Yes, and yeah. Okay, so there's another difference between the replicative studies and the original study, and it's that the replicative experiments removed some highly similar images in the stimulus side. So they actually had 388 images in total. Because we have some images like this, you can't really see the difference but they are two different images, two separate images in our original study. So that might influence the most strict condition where k equals 1.
Nice.
So, but I haven't checked this. Yeah. And this is a potential reason. Yeah. And then I want to go back to the MDS plot to show the error pattern. And the question is, what images are easy or hard to classify? So this is the MDS plot coded by matching rate. So a darker color means higher matching rate, and a lighter color means a lower matching rate. So you can see around the center of this space, MDS space, and where the dots, sorry, here each dot means one image. And so around the center of the space, where the dots are clustered together, and the matching rate tends to be lower. And at the edge where the dots are distant from each other, the matching rate tends to be higher. And I will show you some examples. So I selected the most extreme images and coded by red and green. So red means matching rate 0. So yeah, the matching rate is 0. And green means the matching rate is very high. So here, as now predicted, the Eiffel Tower image, Eiffel Tower is there and showing a very high matching rate. And from other images, you can see, it's probably, to me, it's probably easy to describe even under a very hard condition where SOA is 67 milliseconds. So Zoe?
Yeah, sorry, just to clarify, in this plot, what are the points? Are they the centroid embeddings?
No, they are the matching rate for each image. So we have 420 images in total. And for each image, we have 10 participants, which allowed us to do 10 matching, or say 10 tests in total. And the matching rate means the proportion of successful matching.
Yeah, but I think, Zoe, you are asking whether we have actually plotted the centroid's location and then projected
The images themselves.
lower.
Sorry.
So you asked whether we plotted the centroid location in the high dimensional space and then projected it back to the lower dimension or something like that, right?
Yeah. Or I guess that was what I thought initially what this was, but.
Oh yeah, initially this was calculated from the cosine similarities between images. Yeah, so based on centroid, yes, the distance.
Not necessarily. I mean, this is based on similarity matrix.
Yes, it's not very. Yes, I didn't mention that. Yes.
Right. So Zoe, what you said is actually interesting point. I don't know. We need to check, but probably centroid position and the similarity matrix is not really one-to-one, probably. You can imagine that the center of the centroid is extremely isolated from all the points. In that case, that one will be very distinct from everything. And that locates probably very far in the edge of this kind of representation. So we don't know. It may be actually useful.
Yeah, we haven't checked that. So the MDS itself, yeah. But from the examples, we can to me maybe you can. It's hard to imagine the 67 millisecond condition, but to me these images should be easy to describe in detail. And here are some examples of low matching rate. Also, as we predicted, this scatter patch or white noise is there. And again, it might be hard to imagine, but to me, these images might be hard to describe under a very hard condition. But we will take a look of the response at the response words in detail. So for these three, this one, and this one that look very easy to describe in detail. And let's take a detailed look of the response, actual response words. So we can see that these are the most frequent response words, but the report frequency is not very high. You can see no one say water skiing or the detailed activity. And here no one says flower. Here no one says diving or something. Yeah. So I think the details are hard to describe under a very hard viewing condition. Yeah. And again, these four at the bottom, these four images at the bottom, they look very different, but they are clustered together. So let's take a detailed look. You can see the response words tend to be very nature related, like flower, water, animal, or these are related to natural things. So as I mentioned before, natural things might be a loose cluster. So these images are clustered together. And yeah, that's a potential issue that MDS based on cosine similarity might not be able to show the distance of every single image correctly. But I haven't checked this. Yeah, we may need to convert cosine similarity in a different way into distance. And here I want to emphasize that low matching rate is a separate issue. So easy to describe doesn't guarantee a high matching rate. So for example, the cat image, if we have a set of cat images, it might show a low matching rate because the matching rate also depends on the other images in the stimulus set. Yeah. And in Liet's results, they also used black and white and blurred images. So here are the, only 2 of the experiments used this black and white and blurred images. So I run the analysis and show the results here. You can see that it's quite similar between the intact condition and black and white condition. But the blurred images showed much lower matching rate. And I think it's understandable because here you can see it from the example. And for the intact and black and white images, they look different, but you might want to use similar words to describe them. But for the blurred images, they might be different. Okay, so here are some take-home messages. So from this methodology, we want to argue that a free report paradigm is able to capture conceptual experiences. And by this, we can turn the experiences into a similarity matrix, and that can be used for further analysis on qualia structure. That's the point. And I have a brief additional story based on this work. So we should have, it's just a few minutes. And 2 years ago, we collected some verbal descriptions on emotion images and videos with different instructions. And when I presented the results in the qualia structure grant meeting and somewhere else, I received a lot of criticisms from different people because word vectors are not sensitive to emotion words. But after doing this analysis, at that moment, I could not validate the usage. So I cannot show whether I was wrong or I was right. I don't know at that moment. But now with this, we can reanalyze the previous data, and yeah, the performance is much better than chat performance. But yeah, with a small stimulus set, it's at least it's promising. So the point is, some data or some project that you thought might be a dead end might be useful in the future at some time. Yeah, so that's a personal story I want to share. Yeah, and that's all.
All right, thank you. Okay, before we take the break, I just wanted to say thank you everybody for joining, and you know, if you have any questions, we'll start a deeper discussion after a 5-minute break. And I wanted to say that maybe, for example, you know, Chihiro's dream, Chihiro, you know, Hiroshige's dream experiment results based on the verbal response, or Ryuta's, you know, sports Fourier characterization by words, and also Ryohei's, you know, Fourier under the drunken state. Potentially, you know, on the emotional image is pretty much applicable or kind of easily adaptable with this kind of methods as a starting point, and it may not be super time consuming. So we'll take a break and then come back in 5 minutes. All right, can I share the screen?